So this was our workflow in the previous video. Our workflow in the previous video was this four-step process. Represent the system as an augmented matrix, row reduce that augmented matrix, turn the reduced augmented matrix back into a system, and then solve the system by back substitution. That has been our process up to this point. Now, what we're going to talk about today and tomorrow is a way to continue to use linear algebra, a way to continue to use matrix techniques to do this final step in matrix form as well. So rather than having to translate the augmented matrix back into a system to do the back substitution, we will do the back substitution while the problem is still represented in augmented matrix form. So that is going to be the focus of today's lecture and tomorrow's lecture, taking this entire process and representing even the back substitution step using matrices instead of traditional equations containing variables. To that end, we're going to talk about an algorithm today, which is called Gauss-Jordan Elimination. Gauss-Jordan Elimination. And to that end, once again, I have to give us some terminology so that we can talk about Gauss-Jordan elimination effectively. So Gaussian elimination was the process of taking a matrix and writing it in row echelon form. And row echelon form had the following two properties. We needed rows containing zeros to be shuffled to the bottom. We also needed the pivots of each row of the matrix to have this sort of staggered staircase pattern, where as you move down the rows of the matrix, the pivots move over to the right. Now, reduced row echelon form, RREF for short, is describing a matrix that is in row echelon form that satisfies these two properties, and some extra restrictions have to be satisfied as well. The first additional restriction that has to be satisfied by a matrix that is in reduced row echelon form is that all of the pivots are equal to exactly 1. All your pivots have to be equal to exactly 1. You're not allowed to have a pivot of 2. You're not allowed to have a pivot of 8. You're not allowed to have a pivot of 5. Your pivots have to be positive 1 exactly. That's the first requirement. Additionally, your pivots, these pivots of 1, must be the only non-zero entry in that entire column. So here's an example of a matrix that is in reduced row echelon form. 1, 1, 1 on the diagonal, zeros everywhere else. This matrix is in reduced row echelon form, and let's confirm that that's true. So this particular matrix has 3 pivots. Here is the first pivot in the first row. Then in the center is the pivot in the second row. And then in this final entry is the pivot in the third row. Now notice all 3 of the pivots are equal to positive 1 exactly. Additionally, if I look at those ones and I look below the 1 and if I look above the 1, I can see that every other entry in the matrix with these ones, all of those entries are 0. So this 1 is the only non-zero entry in the entire column. This matrix is in reduced row echelon form. Here is another example of a matrix that is in reduced row echelon form. We have 1, 0, 0, we have 0, 1, 0, and we have 0, 0, 0. This is also fine. In this case, we do have a row containing all zeros, but it has been shuffled to the bottom of the matrix, so that's okay. We have 2 pivots in this matrix. We have this one here in the top left. We have this one here in the center. And there are no other non-zero entries above or below those pivots. Additionally, both of those pivots are equal to 1, as opposed to any other value. Here's another example. This matrix 1, 0, 1, 0, 1, 2, 0, 0, 0. This guy is also in reduced row echelon form. And let's see why. First of all, we have a row of all zeros, but once again, that row has been shuffled to the bottom, so that's okay. This matrix only contains two pivots inside of it, still. The first pivot here in the upper left corner, because this is the first non-zero entry that we encounter as we look into the first row. The second pivot is located right here in the dead center of the matrix, because this is the first non-zero entry that we encounter in the second row. And then there are no pivots at all in the third row, because the third row is just all zeros. Now, both of the two pivots that we've identified are equal to +1 in their value. Additionally, when we look up and down from those pivots in the matrix, we can see that those pivots are the only non-zero entries in their column. So all the requirements have been met for this matrix to be in reduced row echelon form. This third column isn't having much of an impact because this third column doesn't have any pivots inside of it. So much of the restrictions for reduced row echelon form do not care about columns that don't contain any pivots at all. So this third column is kind of free to do what it wants at this moment. So some examples, some counterexamples, matrices that are not in reduced row echelon form. I could give us, for example, 2, 0, 0, 0, 1, 0, 0, 0, 1. This guy is close, but the issue is that this pivot right here in the top left corner is not equal to 1 exactly. So that is the issue with this particular matrix, and that's why it's not quite in the right form at the moment. This guy is in row echelon form, but he is not in reduced row echelon form. Reduced row echelon form, all the pivots have to be equal to 1 exactly. Let me give you another example of a matrix that is not in reduced row echelon form. 1, 0, 1, 0, 1, 2, 0, 0, 1. In this case, we have a problem. This guy is in row echelon form, but he is not in reduced row echelon form. And the issue is these two values here in the corner. In this particular case, as we look into this particular matrix has three pivots. This first pivot here in the top left corner, this pivot here in the middle of the matrix, and this pivot here in the bottom right. Now, if I look above and below those pivots in the matrix, I can see that the first two columns are fine. All the entries and below and above the pivots have been cleared out. But in the third matrix, we see that there are non-zero entries in the same column as this pivot. So that is a problem, and this matrix is not in reduced row echelon form. So this matrix would not count. So once again, reduced row echelon form and the requirements for that form might seem a little strange and a little bit arbitrary, but reduced row echelon form is meant to once again capture what a system of equation looks like after you have performed certain steps to solve that system. So in this particular case, reduced row echelon form is meant to mimic the appearance of a system of equations after you have eliminated the variables and also after you've completed all necessary back substitution. So let me go back to one of our previous lessons just to sort of showcase that. So for example, in this problem from yesterday's lecture, we had our augmented matrix and we got it into row echelon form. Row echelon form being this guy right here. And from row echelon form, we were able to take this last equation and solve it for a single value of z. A single value of z equals 1 in this case. After we found the value of z, we started the back substitution process. And in the back substitution process, we got three equations from that back substitution. Three extremely simple equations. The first equation being that the x must be equal to 2. The third equation being that the y must be equal to -1. The final equation being that the z must be equal to +1. Now, if we take this system of equations and write down the augmented matrix that represents this highly solved, highly simplified system as it exists right now, the augmented matrix corresponding to that guy would be 1, 0, 0, bar 2, 0, 1, 0, bar -1, and 0, 0, 1, bar +1. So notice that after both the elimination and the back substitution has been completed, the system of equations has an augmented matrix that is in reduced row echelon form automatically. So reduced row echelon form captures this highly simplified format of an augmented matrix after elimination has been completed and also after back substitution has been completed. Now, once again, Gauss-Jordan elimination is the process of taking a matrix and rewriting it in reduced row echelon form, in the same way that Gaussian elimination was to rewrite it in row echelon form. So once again, this is just the process of solving a system by elimination, but this time we are also doing the back substitution step using matrices as well. We are also doing the back substitution using a matrix. So here's a little visual, like a little diagram to help to showcase sort of what's happening here. We have a system of equations which can be represented by an augmented matrix. If you're performing the process of elimination on that system, that's equivalent to performing the process of Gaussian elimination on that augmented matrix. The status of the system after you've done the elimination and before you've done the back substitution, that's equivalent to the status of the matrix when it is in row echelon form. Now, back substituting in the system of equations is the same thing as going through the process of Gauss-Jordan elimination on the augmented matrix. And then the appearance of the system after you've done the back substitution is equivalent to the appearance of the matrix when it is in reduced row echelon form. So that is how these two concepts link up to each other. Every single action that you do on the system has an equivalent in terms of the action that you perform on the augmented matrix. So let me demonstrate the Gauss-Jordan elimination algorithm on the following matrix. And to start with, again, I'll do it by hand for folks who don't have a graphing calculator who can do it. And the first step of the process is just to perform regular Gaussian elimination, the same Gaussian elimination that we've been using since a couple of lessons ago. So for example, I will add -3 copies of row number 1 to row number 2 to eliminate that 3 from the first column. And if I do that, the matrix becomes everything that it was before, except in the second row, we have 0, we have -1, we have -5, and we have -21. Hopefully that's right. Subsequently, let's go ahead and eliminate this 2 in the first column. So to get rid of that 2, I'm going to add -2 copies of row number 1 into the third row so that the 2 will be canceled out by that -2. I'm canceling out that 2, so it's gone. Then I have -4 plus +1, so that's -3. I've got -4 plus -1, that's -5. I've got -10 plus -1, that's -11. So that's our status right now. And then we're going to go ahead and continue the process by eliminating this pivot underneath the -1 here in the center of the second row. So to get rid of this -3, I'm going to cancel it via a +3. So in order to get a +3 in this central position, to cancel out this -3, I will scale the second row by -3. Copy paste everything except for the third row, which is being modified, canceling out this entry in the second column. Then we have 15 minus 5. 15 minus 5 is 10. Then we have 63. 63 minus 11, which is 52. As of this moment, we now have the matrix in row echelon form. So now let's begin to take the process of writing it in reduced row echelon form. So the next move is to rescale the rows to take all the pivots that are currently in view and turn all of the pivots into +1. So as of this moment, the first pivot in the top left is +1 already. Fantastic. The second pivot in the middle of the matrix is -1. So I'm going to have to fix that by rescaling the second row to turn a -1 into a +1. So I can, for example, scale row 2 by a factor of another copy of -1 to turn this negative into a positive. Additionally, if I want to deal with this pivot 10 in the third row, then I would have to divide by 10 to turn that into a 1. So I will go ahead and at the same time scale row 3 by applying a divided 10, by applying 1 over 10. If I scale the second row by a -1, that's going to have the effect of flipping the signs. So -1 becomes +1, -5 becomes +5, -21 becomes +21. And if I divide the entries in the third row by 10, that's going to shift the decimal point. So that's going to turn the 10 into a 1, and that's going to turn a 52 into a 5.2. I'm not in the mood to deal with fractions too much today, so let's just do decimals. The last thing that we need to do is clear out these entries above the pivots in the matrix. We've already cleared out the entries below the pivots in the matrix, but now we have to cancel out the entries above the pivots in the matrix. So we're going to do that much the same way that we did Gaussian elimination. We're going to do that by by scaling rows and adding them together. The major difference is that with Gaussian elimination, we started on the left end of the matrix and we worked our way toward the right. The major difference here is we're going to start on the right side of our matrix and we're going to work our way toward the left as we clean those non-zero values out. So step number 3, use row scaling and addition to clean out the entries above the pivots, working from the right to the left. So for example, as I start this process, I'm going to start with the pivot that's furthest right in this matrix. I have 3 pivots in this matrix, and the pivot that's furthest to the right is the pivot that's located right here at the bottom of column 3. So I'm going to start in column number 3, furthest to the right, and I'm going to use row scaling and row addition to clean out these 2 entries above the 1 in that third column. Okay, it's now the next day that I'm returning to this problem. So where was I? I want to use row scaling and row addition to eliminate this 5 above the pivot of 1 in the third column. So to eliminate this 5, I'm going to scale row 3 by a factor of negative 5. Negative 5 so that I get minus 5 here to eliminate the positive 5 directly above it. Now, notice that when we perform this action, these two values in column 1 and column 2 of the matrix will not be affected by this action because when I scale row 3 by negative 5, these two zeros in the bottom left corner of the matrix are still going to be 0. And when we add them up into row number 2, that added 0 is not going to have any effect. So really the only thing that has the potential to change at this juncture is the value directly above 1, which by design has been canceled out and turned into 0. And then we calculate the value in this constants column where we have 5.2 times negative 5 combined with 21, which is negative 5 in that position. To get rid of this positive 2, I want to create a value of negative 2. And since my pivot is equal to 1, I can do that pretty simply. Just scale row 3 by minus 2 and add up there to row 1 to cancel out that 2 value. So if I do 5.2 times negative 2, and I combine that with positive 5, that's a value of 5.4 negative. Okay, so I have now cleared out all the entries above the 1 in the third column. Having done that, I'm going to scooch over to the next column here on the left, column number 2, and I'm going to try and clear out this entry above 1 in the second column. So to that end, I'm going to create a pair of opposite terms that will cancel out when added together. I'm going to go ahead and scale row number 2 by a value of minus 2. So I'm going to do that. I'm going to add that up into the first row. So once again, because row 2 has so many zeros inside of it, not many of the entries in row number 1 will be affected by this action. The only entries in row number 1 that will be affected by this action is the entry directly above this 1 in column number 2, which is going to be canceled out by design. And then this outputs column might also be affected by this action. So let's see what happens in the outputs column when I take negative 5, when I multiply that by negative 2, and when I add that to negative 5.4, 4.6, positive. So now the process is complete, and we can treat this as our final answer. Now, once again, I'm just demonstrating that process for those of you who don't have access to a graphing calculator or are curious to have some sense of what the graphing calculator is doing on the back end when you perform a row reduction command. That concludes today's lesson. Today we talked about a process called Gauss-Jordan Elimination, which is an algorithm that is applied to matrices, typically the augmented matrix for a system of equations. When we perform Gauss-Jordan elimination, the purpose of that algorithm is to take a matrix and write it in reduced row echelon form. Reduced row echelon form is like row echelon form with a couple of additional restrictions. All the pivots in the matrix are equal to exactly 1, and those pivots are the only non-zero entries in their entire column. And this is just meant to mimic the appearance of an augmented matrix for a system of equations after this process of elimination has been completed and also after the back substitution has been completed. The Gauss-Jordan elimination algorithm starts by performing regular forward Gaussian elimination, as we learned about 2 lessons ago. Then you go into that row reduced matrix, you rescale all the rows to turn pivots into 1, and then you go backwards through the matrix from right to left and use row scaling and row addition to eliminate the entries above the pivots in the matrix.